Okay, good afternoon. So we will continue with our discussion with the semaphores. So we have talked about how we can use the semaphores, and we have seen how we can implement the semaphores in kernel, okay, like this. So this is the pseudocode showing the kernel implementation of semaphores. So of course this is a typical implementation and just one sample implementation. All the implementation does not have to be like this, okay? So we have discussed that in the previous lecture. And so before that we had actually discussed also how we could use the semaphores in our applications to solve the synchronization problems. So semaphores are actually quite powerful tools, so you can use them to solve various synchronization problems, including, for example, the mutual exclusion problem, critical section problem that requires only one process to be in the critical section, okay? It also helps us to solve other synchronization problems, like, for example, enforcing a process to wait until some other process did something and caused an event to occur, okay? So semaphores can be used to solve various synchronization problems. And in project 2, actually, you will use them to solve a synchronization problem. So now let's look to the issues regarding the semaphores. They are powerful, but you have to be also quite careful in using the semaphores. So what can be the problems? Here we see a problem here, deadlocks. So if you are not using the semaphores carefully, then we can have a deadlock in the system. So what's a deadlock? Two or more processes are waiting indefinitely for an event that can be caused by only one of those waiting processes, okay? So you have two or more processes. Each is waiting for something that can only be caused by the waiting processes. Hence, that event will not be issued, okay? That event will not happen. So those processes will wait forever, okay? So this is the deadlock situation. So we can have deadlocks in the system if we use the semaphores in an incorrect way or in a different way and so on. So let's look to an example here. Let S and Q be the two semaphores that are initialized to 1, okay? So we have two semaphores, S and Q, okay? Two applications or two processes will use them, P0 and P1. Assume P0 is using them in this manner, okay? So P0 first does a wait operation on semaphore S and then does a wait operation on semaphore Q, okay? Assume this is the case, and then it will do a signal on S and then signal on Q, okay? In between it can do something, all right? Like, for example, executing critical section code. And let's look to P1. It's also doing similar thing, but it first does a wait operation on semaphore Q and then does a wait operation on semaphore S and then does something and then does a signal operation on Q and signal operation on S, okay? Assume these are two programs that are coded in this manner, okay? So this may, however, can cause a deadlock. Okay, if you run those programs concurrently, this may cause a deadlock. Of course, not all the time, but from time to time, okay? So, for example, let's see how we can have a deadlock. Assume P0 is run by the kernel scheduler, okay? It is now started and running in the kernel, in the CPU. So it issues a wait system call on semaphore S. So what is the initial value of S? It is 1. So do you think this wait will cause or will block P0? No, right? It will not cause P0 to be blocked, so it will return from wait. But as a result, S will be decremented to 0, right? So it is now 0 after wait is executed. So P0 can continue running, but assume just at the time we had a context switch. Assume just at the time we had a context switch here. All right, so that this process is suspended, P1 is run, okay? So then assume P1 starts running. So what is it is doing? It is just issuing a wait system call on semaphore Q. What is the initial value of Q? It is 1, right? So therefore, this wait will not cause P1 to block. So P1 will be able to continue executing the next statement, which is a wait operation on semaphore S now, okay? What is the value of the semaphore S at this time? 0, right? So what will happen then when you issue a wait operation on such a semaphore? Right. So process P1 will be blocked by the kernel, right? It will be blocked, so it will not be able to return from wait. So it is just waiting here. Waiting for what? Waiting until somebody issues a signal operation on S. Who will issue a signal? Here, process P0 can issue a signal, okay? So it is waiting, so it is blocked, so kernel may decide to run another process, so it may be this process again, so it had been suspended at this point, so it will continue from this point, right? So what is the next statement that it will run? The next statement it will run is this one, waiting on Q, semaphore Q. So it performs a wait operation on semaphore Q. So what's the value of Q? 0, right? So this will cause that process to block, right? So it will also be blocking now. So it cannot continue. So now what we have, now this process blocked and that process blocked. So this process is waiting that process to signal on Q, and that process is waiting this process to signal on S, right? So that means these two processes that are waiting now, blocked, okay, sleeping, are waiting each other. Okay, they are waiting each other, and therefore that event will not happen. None of these processes will be able to issue a signal. Therefore, those processes will wait forever. This is a deadlock situation, okay? And you may fall into such situations with semaphores that are enforcing a process to sleep and so on. Then we can have those situations. So actually, if we would reverse those two statements or those two statements, we would not have that deadlock situation. The deadlock occurs here is this, because the order of requesting the resources here, the semaphore resources, is different than here, okay? First, S is wanted, then Q. Here, first Q is wanted, and then S, okay? This is causing the deadlock. If we would reverse the order in the first process there, then we would not have this situation, okay? So you have to be careful about those kind of issues while programming with semaphores, okay? These examples shows this fact. Is it clear? All right, now let's look to other issues. Starvation. Sometimes starvation may happen if, for example, the semaphore implementation inside the kernel selects the processes in, for example, last in, first out order. So that may cause a process to block on the semaphore queue, all right, can be, for example, may never be removed from the queue, okay, in which it is suspended. Then that process will always be sleeping, all right, will not get any service, okay. So this is starvation, and sometimes we may also fall into those situations, okay. And priority inversion, scheduling problem when lower priority process holds a lock needed by a higher priority process. So we may have in the system several processes with different priorities. Assume we have a high priority process, medium priority process, and low priority process, okay? Assume now we have the high priority process waiting, all right, for a semaphore that is held by a low priority process, okay? So a low priority process did a wait operation on a semaphore, binary semaphore earlier, and the high priority process, assume is waiting, did a wait operation on the same semaphore and waiting for the low priority process at the moment, okay? So now what can happen? Assume we have also a medium priority process in the system running, okay? So then the kernel will schedule which process? Even though there is a high priority process, it is waiting for a low priority process, okay? Low priority process, for example, can be in the critical section now. It is executing, okay? It is not blocked. It is executing, but it is holding the lock. It's holding the semaphore, okay? And high priority process is waiting that, okay? Normally what will happen? Since there is a high priority process waiting, you should run that low priority process immediately so that it can actually get rid of the critical section, get out of the critical section, okay? And release the lock so that high priority process can start running, okay? But what will happen in a system that is applying priority-based scheduling? We have also a medium priority process that wants to use the CPU. Since the high priority process is in the blocking state, the kernel scheduler will select the medium priority process and will run it in the CPU, and low priority process will not be able to run in the CPU. It will not get a chance to use the CPU and release the lock. So then what will happen? You will enforce that high priority process to wait because of a medium priority process is running, okay? So this is called priority inversion. Actually, if you consider the priorities, this should not happen. A medium priority process should not cause a high priority process to wait, okay? But it may happen if you use the semaphores and so on. So priority inversion can happen. There are some solutions to that, okay? Like, for example, inheriting the priorities and so on. The low priority process can inherit the priority of the high priority process. In this way, the medium priority process will not come ahead of the low priority process, okay? This may be a solution. So these are some problems that we may face if you use the semaphores. So let's look now to some problems. Do you have any questions so far about the semaphores? So far you should have understood how we can use the semaphores and how they are implemented, okay? So if you have any questions about that, please ask me now. Okay. So now let's look to some example problems, how we can solve them using semaphores. We will look to some example synchronization problems and their solutions, how we can solve them using the semaphores. We will see three problems: bounded buffer problem, readers and writers problem, and dynamic philosopher problem. These problems are fictitious problems, okay? For example, especially dynamic philosopher problem is not a real problem, okay? But it is important to show how the synchronization tool is solving it, whether it can solve it or not. Because if you can solve that model problem, okay, you can also solve some other real problems that look like this, okay? So therefore they are important. So let's look to the first problem, bounded buffer problem, and how we can solve it using the semaphores. So the problem actually the one that you already know. So we have a producer that is producing items and a consumer that is consuming items, right? And we have a bounded buffer here in between that's shared, that can be accessed by both producer and consumer. It can be just a global variable, and those can be threads, or it can just be a buffer in shared memory, and those can be processed, okay? So we have a bounded buffer, meaning that it can hold at most some number of items. Let's say buff-sized number of items, okay? If you try to put more items there, you will not be able to do that, okay? You should not be able to put more items than the buffer size here. So assume we have buff-sized slots available initially. So now, how can we implement a solution to this so that this producer consumer will run concurrently, access to the shared buffer, and this access should be in a controlled way, so that you are not corrupting the data and so on. You do not have inconsistent state. So access to the buffer should be synchronized. This is access to that is a critical section that is protected, that is to be protected. Access to the buffer should be, in other words, in a mutually exclusive manner, okay? So this is one thing that you should provide in your solution. And the other thing that you should provide is this. The producer should not produce more items and should not try to put those items into the buffer if the buffer is full. Then at that time, the producer should simply sleep until consumer retrieves an item and there is one slot available that is empty in the buffer. At that time, the producer should be waken up and can put a new item, okay? And similarly, the consumer, when the buffer is empty, should go into sleep until producer produces something and puts that into the buffer, okay? So these are the synchronization requirements. We want to implement two programs, producer and consumers, that are sharing a buffer and that are behaving in this manner. How can we do that? Previously, we have seen a solution that was using busy waiting, right? That this was just checking the inside the while loop, the buffer, the count variable, and so on. But now we will see a solution that is using semaphores, okay? And that solution is more efficient because if producer cannot put more items here because the buffer is full, then it is sleeping. It is not wasting CPU cycles by just busy waiting, okay? So how can we implement the solution? So we have a buffer, shared buffer. We have to implement that. Assume the shared buffer can hold at most n items. So the size of the shared buffer is n slots, okay? Each slot can hold one item. So we also define a semaphore mutex, okay? That is initialized to 1. So it will act as a binary semaphore, initialized to 1, so that it will be used to protect the buffer that's shared, okay? So that with that, we will make sure that one process at a time is accessing and modifying the buffer, okay? Putting an item or retrieving an item. And we have two other semaphores, full and empty. They are counting semaphores, okay? Full is initialized to 0 and empty is initialized to n. What is the full is doing here? Full is a semaphore that is counting actually the number of full slots. Initially, how many slots are full here? 0, right? So therefore, full is initialized to 0. Initially, 0 slots should be full, so full is initialized to 0. And empty semaphore will indicate the number of empty slots in the buffer. Initially, what do you expect that number to be? The empty slots, number of empty slots initially should be 0, right? So, sorry, n, right? There are n empty slots available initially, okay? In which you can put some items. So therefore, empty is initialized to n. N is the buffer size, okay? So now let's look to, for example, at some arbitrary time, we can have such a buffer state and semaphore values. So the buffer has, for example, 4 items at the moment. So the full semaphore will have a value 4, and the empty semaphore will have a value 6, indicating there are 6 slots available to put new items, okay? So now how can we code the producer and consumer using these semaphores? So this is the code for the producer and this is the code for the consumer. Assume in an endless loop, okay, producer will produce items and put them into the buffer to pass to the consumer, and in an endless loop, consumer will try to remove items from the buffer and consume them, okay? They are doing those in a while loop running concurrently. So then, how should we code the producer? So here, we are showing the code for the producer. Assume the producer has produced an item and has put that item to this local variable, okay? So that now what it will do? It will try to put that item into the buffer, right? But we have to make sure that in our implementation, the producer is not putting the item into the buffer if the buffer is full. How can we understand whether the buffer is full or not? Which semaphore indicates the buffer state, whether there is an empty slot or not? Right, empty semaphore indicates the number of empty slots. If empty semaphore value is 0, that means there is no empty slot, right? What should happen at that time? The producer has to sleep, right? How can we enforce now the producer to sleep if the empty semaphore is 0? How can we enforce it to sleep? Right, we can just issue a wait operation on that semaphore, right? Empty. If empty is 0, then this will cause the producer to go into sleep, right? Otherwise, it will not cause the producer to go to sleep. Producer will return from wait successfully and will continue executing. But as a result, empty will be decremented by 1, right? Do you think it is logical? Yes, because you will put an item and the number of empty slots will be 1 less as a result of that. So this is logical that wait is actually decrementing the count by 1. It's okay, right? So now let's look to the next statement. So assume you have passed that point. So now assume you had 1 empty slot available, so you did not block here. So you will continue now. What you will do as the producer? You will go ahead and touch the buffer and put the item there. The buffer can be implemented as a linked list, maybe, okay? That means you would like to add a new item to the linked list. So linked list is a shared data structure. While you are adding something to that, another process should not touch to that, right? How can you ensure that? Right. So now we use the mutex variable, okay, to provide actually exclusive access to the shared data, which is the linked list of items as the buffer, right? So therefore, we have to do a wait operation on the mutex, which will allow us to go further if mutex value is 1. That means nobody is actually touching to the buffer. But if the mutex value is 0, that means somebody else did a wait operation earlier and still in the critical region did not do a signal operation yet, okay? Somebody else did a wait operation and manipulating the buffer at that time. So mutex value is initialized to 1. So the first process that does a wait on that will be able to pass, return from wait, and go ahead and enter the critical region. But another process will wait. So therefore, we are protecting the access to the shared buffer using a mutex variable, okay? So a process should do a wait operation on that mutex and then go ahead and access the buffer. So if the mutex value is 1, that means nobody is actually accessing the buffer at the moment. Lock is available. So you acquire the lock and you manipulate the buffer. Otherwise, you are blocked here. You are blocked here until the other person, the other process, finishes its manipulation with the buffer and issues a signal operation on the respective mutex. Then you will be unblocked and will be able to execute your critical section, which is touching to the shared buffer, okay? So assume you passed that point as well. Nobody was in the critical section. Now you are adding the item to the buffer, okay? So there you are touching to the shared data. But here we are sure that nobody is actually touching to the shared data. And when we are finished with that, what we will do? We will just issue a signal on the mutex, okay, protecting the buffer, so that now somebody else, if it wants to manipulate the data, can manipulate the shared data, okay? So we issue a signal operation on the mutex, okay? So that somebody else, for example, the consumer may be waiting around here to enter to the critical region and remove an item, so it will be able to remove the item after you issue a signal, okay? But we also do this. Signal full. Full is a semaphore indicating the number of full slots in the buffer, right? Since you had put an item here, you have to increment that value, right? That semaphore represents the number of full slots. When you put a new item, the number of full slots should be 1 more, right? So therefore, you have to issue a signal operation. Signal means that incrementing the semaphore value. If there is nobody sleeping, of course, on that semaphore. If, however, there was somebody sleeping on that semaphore, that means, for example, a consumer might have issued a wait operation on full semaphore, and if the full value was 0, that means no item in the buffer, no full slot in the buffer, then the consumer is put to sleep, right? So at that time, that means the full value is 0. So if you issue a signal on a semaphore that has a value 0, what will happen? What was the semantics of the signal operation? So if there is a sleeping process, that process has to be waken up. Okay? So that means there can be a sleeping process. So as a result of this signal, that sleeping process will be waken up. Okay? That was waiting here, and then we'll be able to continue. And that's logical, right? Because you have now put a new item here. If the buffer was empty so that somebody was sleeping, after you have put an item here, now the buffer has at least one item. Okay, and your signal should wake that process up. If there is no sleeping process, however, the signal should cause the full count to be incremented by 1. Okay, you may have this situation as well. The buffer may be empty, but there is no sleeping consumer at the moment. Then after you have put your item, do you think it is immediately consumed? No. So as a result, the number of items in the buffer will be 1, right? Since it will not be immediately consumed. Therefore, your signal should increment the full count by 1 in this case. And the full will become 1. It was 0, and there was no sleeping process. When you issue signal on such a semaphore, then full is incremented, right? However, if there were a sleeping process, then that process is waken up. Full is not incremented. Is it clear? And here, for example, if the buffer was empty and there was a consumer waiting here, then what you do, after you put the item, you signal on the full that had value 0. Now that sleeping process is waken up, but full is not incremented. It is still 0, right? Why? Because that's waken up process. Consumer will anyway immediately retrieve the item and will consume it, right? Therefore, the item count actually should not be incremented because it is immediately received. It will be immediately received by the consumer and will be consumed. Okay, so therefore this implementation is correct. What I mean, okay? And let's look to the consumer code now. It's very symmetrical to this. So the consumer, before retrieving an item, it has to first make sure that there is an item, right? So if there is no item, it has to sleep. How can you enforce that? You can just issue a wait operation on the full semaphore, which is the number of full slots. Okay, if it is 0, that will cause that process to sleep. Otherwise, full will be decremented by 1, right? Full will be decremented by 1 because now the number of full slots will be 1 less because you are consuming 1 item. So if you pass that point, that means you did not block on wait. That means there is at least definitely 1 item in the buffer. Then what you do? You want to go ahead and remove the item. Okay. For that, of course, since the item is actually sitting in a shared buffer, right? In a shared linked list, touching to that, removing the item should be atomic to ensure that you go ahead and access after the wait operation. And you will return from wait if there is nobody accessing the buffer. And then you will go access the buffer and remove the item. And then you have to signal on the mutex so that somebody else can touch the buffer. And then you will also signal on the empty count, empty semaphore, indicating the number of empty slots. Since you have retrieved 1 item now, okay, so there will be 1 more empty slot. So the empty semaphore indicating the number of empty slots should be incremented by 1. Okay? And you are done. You can consume the item. And in this way, the consumer and producer process are running concurrently. Any questions here? So this is a solution to the consumer-producer problem. That makes sure that the buffer is touched by 1 process at a time in a mutually exclusive manner. This is one thing, okay? And it makes sure that the consumer sleeps if the buffer is empty until buffer has 1 item at least. And this solution makes sure that the producer sleeps if the buffer is full until the buffer has space for a new item, okay? So this is an efficient solution. Any questions here? All right, let's look to a different problem now, reader-writer's problem. So what is the reader-writer's problem? So again, this is a different problem now. Assume we have this scenario. So assume we have, again, a shared data set. It can be a file, or it can be a shared global variable, shared linked list, or it can be a variable sitting in the shared memory between the processes, okay? Assume we have readers, writers processes that try to access that. What is a reader process? Assume a reader process is a process that just interested in reading the data here, getting the value, not modifying it, okay? A writer process, on the other hand, is a process that can read the value, but also can manipulate the value, okay? For example, consider the star system, right? There you can see your grades for this course, for example. You can just see your grades, right? You cannot update. But I can, for example, go ahead and update, okay? So I am a writer process, and you are readers, okay? So there can be several readers. 100 students can read, should be able to view the output, the grades at the same time, right? So you should allow many readers to read the data set at the same time. And it's okay. It will not cause any inconsistency, right? they will just see the grades, no update and no problem. Okay? But if there is a writer just modifying the data at the moment, during this time you should not allow any reader to read the data. Okay? Otherwise inconsistencies may appear. Okay? So therefore these are the rules to access the data set, shared data set. If there is a writer accessing the data set, it has to be the only process accessing it. No other writer or reader should be accessing the data set. Okay? But however, if there is a reader accessing the data set at the moment, there can be no writer accessing the data set, but there can be other readers that is accessing the data set. Okay? So these are the rules. So we can allow many readers to read the data set at the same time. Okay? But if there is a writer reading or writing it, nobody should be allowed. So then what has to happen? The first reader, for example, that is trying to access the data set should acquire the log. The other readers can just go ahead and read. And then they will finish and so on. And the last reader that will finish reading the data set, the last reader, will release the log. After that, a writer can go ahead and acquire the log. Or maybe for a while later, again, another reader try to access the log. Okay? So the first reader and the last reader should do something special. The intermediate readers doesn't have to be, right? They just go ahead and check if there is a reader, they can immediately go ahead and read. They don't have to acquire a log, right? So now, how can we implement a solution to this problem? So we would like to implement many processes. Some of them are acting as readers, some of them are acting as writers, right? And those processes will run concurrently and access the shared data item with the rules that I have set. Okay? So how can we do that? So allow multiple readers to read data at the same time. Only one single writer can access the shared data, however, at the same time. Okay? So how can we implement the readers and writers? So the implementation that I will describe now have a shared data that can be a file or a global variable. And now it has also an integer, shared integer, not semaphore, read count, initialized to 0. This value, read count, will just indicate the number of readers currently reading the data. Initially, nobody is reading, so it is initialized to 0, okay? And we will have also two semaphores defined, semaphore mutex and semaphore write, okay? Semaphore mutex will be initialized to 1, write will be initialized to 1. So they are actually binary semaphores. They will be used to protect some shared data, okay? So this write will be used to protect the data set, okay? The write semaphore, WRT semaphore, will be used to protect the data set so that we will make sure that if there is a writer, there will be no readers. If there is a reader, there will be no writer, okay? If there is a writer, there will be no writer or reader, okay? So, and what about this mutex here? So write semaphore will be used for that purpose. But what about this mutex here? So that will be used to protect the read count shared integer, okay? Since read count is counting number of readers. When a new reader comes in, the read count should be incremented by that reader, okay? But at the same time, another reader may be leaving, or maybe another reader may come. So there may be several readers that may try to update this variable. So therefore, we have to protect that shared variable as well with another semaphore mutex, okay? So the purpose of this mutex semaphore is to protect that one. And the purpose of this write semaphore is to protect the shared data, okay? Now let's look to the solution. So this is the structure of the writer process, and this is the structure of a reader process. So the writer process job is very easy now. So it will try to acquire the write log, acquire the write semaphore, meaning that it will try to do a wait operation on the write semaphore. If the write semaphore is 1, it will complete wait and go ahead and write the data. Otherwise, if write is 0, that means somebody else did a wait operation earlier, a reader, then the writer will be blocked here. We say that the writer could not get the log, okay? Is it clear? And then, however, if it could get the log, it will be able to perform the write operation, and then it will do a signal operation on the write semaphore. We say that the writer is actually releasing the log, okay? This is the logic. Is it clear? The writer's job. So let's look to how reader is structured. So now, as a reader, for example, the first thing that we should do is we should, for example, we can increment the read count by 1. Since we want to read the data, right? We will be one more reader to read the data. So the first thing that I will do for example, can be incrementing the read count. So I try to increment the read count. Of course, read count is shared by many readers, right? So therefore, access to that should be protected. So before that, I try to acquire the lock, mutex lock. And the way that I do is by doing a wait operation on the mutex semaphore. So if I can pass that point, that means I have acquired the lock. I am the only reader that is trying to update this value read count, right? So assume I passed that point. There was no reader that was actually incrementing the count at the moment. So assume I incremented the count, and I am now at this point in my execution. So what is happening now? I increment the read count by 1. So the read count can be now 8, 7, okay, or 1. It cannot be 0 anymore, right? So if it is 1, what does it mean? What was the previous value? 0. So what it implies? That means I am the first reader, right? So there was no reader before me. If there was no reader before me, that means the lock of the shared data is not acquired yet by any reader. So it's my responsibility to acquire the lock for shared data, right? How do I acquire the lock? I do a wait operation on the respective semaphore, which is the right semaphore, right? So if the read count becomes 1 after I increment the read count, then I have to go ahead and acquire the lock to access the shared data. For that, I do a wait operation on the right semaphore. Okay? Is it clear, the logic? So then, here I can get blocked because there may be some other process writing. A writer process may be manipulating the shared data, so I may get blocked. Or if there is nobody actually touching to the shared data, then I will return from wait immediately, right? And what I will do? I will go ahead and perform the reading. However, I should also release the lock on the read count, so that another reader may try to increment it, okay? So I signal on the mutex semaphore as well, and then go ahead and read the data, okay? A student is now viewing the grades, okay? So after he or she has finished reading the data, what it will do, what the reader process do, it will again, now this time, will try to decrement the count by 1. So of course, read count is a shared variable. Before that, it has to acquire the respective lock. For that, we do a wait operation on the respective semaphore that is protecting this. So if we return from wait, that means it is safe to update this value. So I go ahead and decrement the read count by 1. Okay? And that's it, basically. But I have to do one more check. Read count, as a result, may fall to what? To 0. What does it imply? If the read count is now 0 after decrementing. Yes, that means I am the last reader. There is nobody else reading the data. So I should release the lock of the shared data so that another writer can go ahead and read it, right? So if the read count becomes 0 after decrementation, then I signal on the right semaphore. That means I am releasing the lock of the shared data, right? So this signal is necessary if the read count has become 0. Then what do I do? Since I decremented it, so I finished my operation on the shared read count variable, so I can also signal on the mutex variable that is protecting the read count. Okay, and I am finished as the reader. Is it clear? All right, any questions? So let's look a little bit more to this example. So if, for example, the first reader has acquired the lock and it is now reading, what happens if a writer arrives? The writer will block where? Right here, right? That writer process will just wait there. What about a reader process? If I was reading, another reader process actually would like to read data. So it will start executing from here. Do you think will it be blocked or not? No, right? So it will be able to pass those points, right? And it will not enter to here because read count will no longer 1. So it will be also reading data, okay? So now let's look to this case. Assume now the writer is writing actually the data. It holds the lock. So assume it is executing in this region, okay? So a reader would like to access the data. So it starts from here. So wait mutex successful. It increments the read count. It sees the read count 1. And now it waits here, right? Is it clear? Okay. So now assume another reader comes in. What will happen? It will start from here. So it will do a wait operation on the mutex. Do you think it will return from there or not? it will be blocked, right? Because the first reader did not actually do a signal yet on the mutex. It will be blocked here. Another reader comes in, it will be blocked there, okay? All the other readers will be blocked here, and that's fine, no problem, okay? As soon as this writer actually finishes executing, okay, and does a signal on the write, releases the lock, so that first reader will be returning from wait, and will do a signal on the mutex, and then we'll go ahead and read the data. That signal will wait another reader that was waiting, will wake up, sorry, another reader that was waiting here. That other reader will increment the read count, will not jump to here, will come to here and do a signal operation. It will wake another reader, okay? In this way, the readers will wake up each other, and they will all be able to enter the critical, they will all be able to read the data. Is it clear? Okay, so this is another synchronization. This was another synchronization problem that can be solved using semaphores in this manner. Okay. So let's look to a different problem, dining philosophers problem. Okay. Any questions so far? So again, this is a model problem. Okay, it is not a real problem, but it is good to actually test the synchronization tools. If you develop a synchronization tool like Semaphore or some other tool, if you can solve with that tool this problem, that means you can solve many real-life problems, because those real-life problems actually look like to this problem, okay? So what is this dining philosopher problem? So assume we have 5 philosophers around the table, okay, that they would like to eat, for example, spaghetti, right? And they have, assume there are 5 forks or chopsticks available in the table, okay? So one fork, another, okay, 5 forks. Assume this is the rule. Whenever a philosopher would like to eat, okay, it requires 2 forks. Okay, don't ask why it is like that. Okay, this is just the problem definition. Okay, so it requires 2 forks to eat. If it can hold those forks, it can go ahead and eat. Otherwise, it has to wait until those forks are available. Okay. So assume a philosopher needs 2 forks to eat. Forks are now like resources. So these forks are like resources, and the philosophers are like processes. A process that would like to do something, okay, need 2 resources, okay, left fork and right fork. If that process can acquire them, then that process will be able to continue. Otherwise, that process should be asleep, okay, should be sleeping, waiting until the neighbor puts the fork, that neighbor also puts the fork, so both forks are available, okay. Until that time, that should be sleeping. And assume a philosopher can actually in 2 states, eating or thinking, okay? When it is eating, of course, before eating, it has to acquire the forks, then it can go ahead and eat, okay? And then after eating, it will release the forks. Then it will go to the thinking state. While it is thinking, it will not require any fork, okay? While a philosopher is thinking, it will not need any fork. It will need forks only when it would like to eat. Just at the time, it will try to acquire the forks. If it can, then it will go ahead and be able to eat, okay? Of course, it may not acquire the forks, then it has to wait. It has to wait until the forks are available, all right? Assume these are the rules. How can we implement those processes, okay? So, of course, these processes will run nearly the same code, okay? But each may have a different ID, okay? But since they will behave very similarly, they can run the same code. So now let's look to a solution. A solution to this problem has to have some properties listed here. We want the solution to be concurrent, to provide concurrency. What does it mean? If this philosopher process is eating, okay, do you think that can eat? No, right? What about this one? Yes, that process should be able to eat, that philosopher. If it is not eating, that should be able to eat, right? So either that or that should be able to eat, if they want to eat, of course, okay? So that means the solution should provide concurrency. While this is eating, if that would like to eat as well, that should be eating as well, okay? If your solution, for example, causes only one process to eat at a time, then it's a solution, but it is not efficient, okay? It is not providing the maximum concurrency that's possible, right? Another desirable property is this: we don't want any deadlock, okay? That means, for example, the processes, the philosopher should not wait each other to release their left forks, okay? They should not wait each other forever. And the third property is that we don't want starvation, because we want to be fair to the processes, and we don't have this situation. For example, one philosopher waits forever to eat. Okay, this situation should not appear. Sooner or later, a philosopher that would like to eat should be able to eat. Okay, so a satisfactory, good solution should provide all these. It's not very easy to provide a very good solution to this. We will now provide a very simple solution that solves some of the problems, but is not solving all the problems here. So this can be the solution. Each process or philosopher can execute this piece of code here. In an endless loop, they can be eating for a while and then thinking, okay? And then after thinking for a while, they may want again to eat, okay? So whenever they want to eat, they have to do this. Wait until left chopstick is available. Wait until right chopstick is available. And then go ahead and read, okay? So for each chopstick or fork, we have a corresponding semaphore initialized to 1, okay? So that it can be acquired only by one philosopher. So the first philosopher that would like to acquire that fork, okay, will be able to return from wait. We'll try to acquire the other fork. It can, if it is the first philosopher to do that, it can acquire the fork and then it can eat, okay? And then it will release the forks. This can be simulated how? By doing a signal operations on the corresponding semaphores, right? So you can code the philosopher program in this manner, right? So this provides concurrency. So if, for example, this philosopher I is eating, okay, it can get those forks, meaning that it can perform a wait operation successfully on the corresponding semaphores. But another process or philosopher here, when it wants to perform a wait operation on a semaphore that has a value 0, then it will be blocked, okay? But here, another one can get those forks, can successfully perform wait operation on them, while this had performed a wait operation on them, right? So therefore, that other process can also go ahead and eat, okay? So two processes can eat concurrently with this solution. But the problem with this solution is it may result with a deadlock. How? How do you think it may cause a deadlock here? Yes.
First process starts and does first read.
Right.
Context switch.
Right.
All processes gets only one.
Yes. Exactly. So assume this process runs and performs the wait operation successfully. That means it acquires the left fork. And then a context switch occurs and that process is run. It also acquires the left fork. That process runs left fork, that process left fork, and this process runs and gets this fork, okay? Then again, this first process, okay, run, and now we'll continue with this statement, which is trying to acquire the right fork, but it's already held by somebody else, by my neighbor, right? So I will not be able to do that. And another process that tries to access the right fork now will be blocked, will not be able to get that right fork. So now these philosophers around the table will be in a circular wait situation. They will wait each other to release the right forks, okay? So therefore, this may cause such a situation, which is deadlock, okay? Of course, this will not happen all the time. Maybe very infrequently. It will happen very infrequently, but you are not guaranteed that you will not encounter such a problem. So in 1 out of 100 or 1,000 runs, you may face such a situation, which may be okay for some applications, but it may not be okay for some other critical applications, okay? So therefore, this solution is not perfect. It has some problems, but it provides concurrency, but can result in a deadlock. But it's at least a solution, okay? A solution that does not cause a deadlock can also be provided with semaphores, okay? But we will not discuss that. Any questions? All right. So semaphores are good, very strong tools to synchronize the processes, to solve the critical section problem. But incorrect use of semaphores may be dangerous and may not solve the problem at all, okay? So for example, while using semaphores, you usually do this. You just call the wait operation first and then signal operation. If a careless programmer does the reverse, for example, it performs the signal operation first and then wait operation. And we have a critical section here. What happens? Do you think that we protected the critical section? No, right? So this will not protect your critical regions. So this is wrong, right? This should not happen. So programmer has to be careful. If it has programmed like that, then that program will not work correctly, okay? Or we may have this. A programmer may program it in this way. It does a wait operation on some semaphore mutex, and then again a wait operation on the same semaphore mutex, okay? So actually this should be signal, but it did wrong and it put a wait here after the critical section. So what will happen? Right, so it will wait and so on, right? So then no other process will also be able to acquire the lock, so everybody will wait and so on. So this is also problematic. Or you just put signal or wait and you forget to put the other thing. Again, you will not have a correct solution. So you have to be careful while using the semaphores, okay? So therefore, we need maybe something else, something better than the semaphores, or maybe something easier to use than the semaphores. Of course, semaphores are very powerful. In some situations, you may prefer to use them, but it is good to have something as an alternative. So now we will discuss that alternative thing, okay, in the lecture after the break.